Okay, so let me just give a brief outline of today's lecture. So we'll do a quick recap of the lower bound that we did towards the end of lecture yesterday. And then we will look at gradient descent as well as for smooth functions. So far yesterday we looked at only Lipschitz continuous functions. So the function is Lipschitz continuous, but the gradients themselves may be discontinuous even, right? So today we'll consider the set of smooth functions and see what is the guarantee that we can say for gradient descent. And then we will design a more sophisticated algorithm called accelerated gradient descent, which actually achieves a faster convergence rate than gradient descent for the class of smooth functions. So yesterday for non-smooth functions, we saw that gradient descent was optimal. So there was an upper bound and then there was a matching lower bound. But for smooth functions, it turns out that gradient descent is not optimal. There is a faster algorithm which is accelerated gradient descent. So this is broadly what we would like to cover today. So let's start with like a recap of the lower bound. Okay, so the high-level argument of the lower bound is following. So for gradient descent, we showed a 1 over square root t convergence rate by just assuming that the function is convex and Lipschitz, right? And we want to say that this is the best anything could do without any further assumptions. And the way we'll do it is that we will construct a Lipschitz and convex function which satisfies both the assumptions that were made in the previous theorem, and then argue that any algorithm, for now, like we'll just argue that any natural algorithm which falls into the span following assumption that we mentioned yesterday can get at best only 1 over square root t convergence rate for a specific function, and this is the specific function that will be constrained. So this is like a hard instance that no algorithm can really do better than gradient descent. By no algorithm, I now mean only within this restricted class. But again, like the the argument can be extended towards randomized algorithms without any other assumptions and so on. But for simplicity, let's just consider this one. Okay. So the function is defined as follows. So x is a d-dimensional object. Okay, and d is greater than or equal to t plus 1. Okay, d is the dimension. X is in Rd, and the function is given by the following. So there is a parameter gamma and there is a parameter mu. The function is gamma times the max over all the coordinates xi, where I goes from 1 to t plus 1. So you look at the first t plus 1 coordinates and then pick the maximum coordinate among the first t plus 1. And then there is this mu over 2 times norm of x square. Okay. So this is the function. And the first thing we would like to understand is what are the gradients of this function? Because the algorithm is able to know things about the function f only through this gradient oracle, right? So we want to understand how do the gradients for this function look like. It turns out that the gradients are not well defined for this function at points of discontinuity where multiple things are equal, right? But then it turns out that we can define something called a subgradient, okay, which is well defined. And the subgradient is the following. So subgradient is a set of vectors. So any vector g is a subgradient of the function f at x if it satisfies the following property. So f is convex, and that actually implies that there exists at least some so if we define convexity even using like the 0th order condition, which is f of x, lambda f of x plus 1 minus lambda f of y is less than or equal to f of lambda x, greater than or equal to f of lambda, So for any convex function, g is a subgradient if it satisfies this, and for convex functions, subgradients are guaranteed to exist at every point. Okay. So this is the definition of a subgradient, and let's maybe just focus on this particular function and see what are the subgradients of this function. Okay. The subgradients of this function are given there, but before we go there, so let's define any given x. Let's define the set I of x to be all the indices I such that xi actually achieves the maximum value of xt. Okay, it achieves the value that we are getting here. Okay, so this is the set of all coordinates for such that xi is actually equal to this maximum. Okay. As an example, like if we are looking at all 0 vector, then I of 0 is like all the coordinates because all of them are equal to the maximum. And if I has a unique maximum entry, then the subgradient is contains a unique So this I is just the first coordinate, right? Because that's the unique thing that achieves the maximum. Okay. So the claim is that the subgradient set of the function f at x is given by mu x, which is just the gradient of this. This is differentiable, so this is just the gradient. And then the subgradient of this, which is given by gamma times the convex hull of EI, where EI stands for the ith standard basis vector. So we have only 1 in the ith coordinate and 0 everywhere else. And then only those I, which are the maximizers that we defined here. Okay. So this is the subgradient. And what we have another choice about is how the oracle actually has to return one subgradient, right? And so far we have not made any assumption on which subgradient it actually reveals. And here, if we also have the choice of deciding which subgradient the algorithm, the oracle can actually return, then the oracle returns the following. So given x,
so
yeah.
So this one you're saying that if there's a degeneracy, basically then you just take the first I which is the maximum.
Yeah, so that will be what the oracle will do. Okay. Like the subgradient set contains like all the things. It does not distinguish between first coordinate, second coordinate, and so on. Okay. All the things which achieve the maximum are similar for it. Like I of x contains all the coordinates which achieve the maximum, and this convex hull of these things. This is the actual subgradient set, but the oracle will return only the first one, which is in I of x. So it returns subgradient G is equal to mu x plus gamma times EI star is the minimum in I. Does this make sense? So all we are saying is that anything in this convex hull is a valid subgradient, and what the oracle chooses to return is the EI star corresponding to the smallest coordinate in the support set I of x. So if we just see what happens, so let's say we start with the algorithm starts at 0, right? So the subgradient set, so I of 0 contains all the elements, right? And the oracle will return E1. So let's say we start with x0 is equal to like the 0 vector, right? Then x1, sorry. So grad f of x0 that the oracle returns plus mu times x0, which is 0. Okay. This is the subgradient that the oracle returns. Okay. Now x1 can be anything in the span of these two. And this span is nothing but span of E1. This is actually a subgradient. So let's say it returns, maybe let me call it G of x0. So it returns a subgradient at x0, and it could have returned any vector within this set, but it chooses to return E1, right? So, and then we will have E1 plus mu times 0, which is this. So the algorithm will then have to choose x1, which is in the span of the original x0, and whatever was returned by the oracle, which is G of x0. Okay, and this is nothing but the span of E1. Right, and so Now, if you look at x2, g of x1. So here, either the maximum will be achieved on the first coordinate. So we are querying at a point which looks like this, right? So, and either this could be 1 or -1 or 0, right? If this is the maximum, then the subgradient does not reveal any more information. So there are three choices. So g of x1 is equal to E1 if 1 is in I of x1. Okay, so this is the main claim that I want to make. So the claim is that we are querying at an x1, which is in the span of E1, right? So there is a scalar that multiplies E1, and we are querying the subgradient at x1. And the claim is that the subgradient, according to this definition of the oracle, will be either E1 if 1 is in I of x1. If not, then it will be E2.
Can you just remind again these EIs basically?
EIs are just standard basis vectors. So 1 in the ith coordinate and 0 everywhere else.
1 0 0 0 0 or
Yeah.
0 1 0.
Yeah, yeah. 1 in the ith coordinate and 0 everywhere else. That's EI. So I mean, one way to look at this is that this is actually the inner product of the ith basis vector times x. Right. So the gradient of this is just so is this part clear? Why g of x1 is either E1 or E2? And I mean, this is basically the key to argue that the algorithm will only see one coordinate at a time. Because in the first time step, it's only able to see the first coordinate. In the second time, it's only able to see at best the second coordinate. And in the third time step, it will at best see a third coordinate and so on. So it will see
the minimum that you have done because of that the minimum. So that's why you're seeing one.
That's correct. That's correct. Yeah. Okay, so sorry. So there is also so let's say something. Yeah. So there will be a mu x1 also. Yeah, that's good one. Thank you. Right, and in either case, span of x0, g of x0, g of x1, all of this is contained in span of E1.
So gamma you have taken to be 1.
Yeah, so there also gamma. That's gamma. So yeah, so then this will be an inductive claim that if you look at the queries that you have done till t iterations, the span of all the things will be contained in the first t coordinates, right? And if you look at this function, if you do something only in the first three coordinates, the t plus 1th coordinate will still be 0. So the function value is lower bounded by 0 as long as the t+1 coordinate is still 0. Right? Whereas the minimum value is something else, and that will give us the separation between what the algorithm is able to do, because we are restricting what the algorithm could possibly output, and the optimum, however, is actually strictly negative. And that's what gives us the quantitative bound. But at least like qualitatively, this is the argument that we do. Is this part of the argument clear?
Doesn't this also imply that the convergence crucially depends on the choice of oracle? Because if we, I mean, at least one could imagine trying to spoil this argument by just choosing a different.
That's correct. Yeah. So roughly, it's maybe the rule of thumb in optimization is that if there is something which makes the algorithm unstable, that will appear in the kind of convergence rates that you can get and so on. So here we use the instability in terms of like the gradient oracle, because at two different points it actually returns two completely different things. We can think of like maybe using a different oracle and so on, but there are more information theoretic lower bounds which will work for any oracle. Yeah. So, I mean, if the high level argument is clear, I can move on to, yeah.
No, so you're starting with, okay, so X0 you are starting with.
Yeah.
Okay. So now, so from X0, now you're first finding the subgradient.
Yeah.
And since, okay, X0 is 0, so then it's just the gamma times E1.
Yeah.
Right? So now that is your
that is my subgradient.
That's your subgradient.
Yeah.
And now X1 will be.
Yeah. X1 can be anything. This is the choice of the algorithm.
Okay.
It can choose anything which is in the span of E1, at least according to our assumption. So we are saying that it can take any linear combination of X0 and G of X0.
Okay.
Right. So it can be anything in the span of E1. So the algorithm has a choice to pick anything in the span.
So anything in the span means like an
meaning that, okay, so this is a one-dimensional space, right? So this is lambda E1, where lambda is a any arbitrary number.
Okay.
It could be positive, it could be negative, and so on.
Okay.
And in particular, so if lambda is positive, lambda is greater than or equal to 0, then the subgradient at x1 will be gamma E1 plus mu x1.
Okay.
Because like the maximum here will be achieved at 1 also, right?
Okay.
And if lambda is less than 0, then the maximum will be achieved by this in the second coordinate, because the first coordinate is negative, all the remaining coordinates are 0, right? So the subgradient will return gamma times E2, where E2 is the second basis vector. And the claim is that it doesn't matter which of these two cases happens, the span of x0, g of x0, and then whatever new gradient that we are getting is still contained in the span of E1, E2.
And this x1,
yeah,
is one of the x1.
No, okay. So actually, I try to distinguish. So this is like a coordinate,
okay.
And this is the iterate that my algorithm produces.
Yeah. Okay. Okay.
Yeah.
So this is a new number.
New d-dimensional vector.
New d-dimensional vector.
Yeah.
So this is the x basically at the
First iteration.
First iteration.
Second, yeah.
And that you are saying that x is basically along E1.
Along E1, because that was the only information you got when you queried subgradient at 0, that my function has some subgradient in this direction.
So along E1, but the magnitude you can take to be anything. Basically.
Yeah, you can take to be anything. Gradient descent would take lambda to be negative.
So now the next iteration, now you again find G.
I'll find G at this new point x1.
Yeah, for using x1.
Using x1. And I'm saying there are two possibilities. If I chose x1 such that the first coordinate is the maximum, Then according to subgradient rule, my subgradient will again be, so this term we can ignore for now, the mu x1, because it's smooth. So it will be in the even direction if the first coordinate is one of the maximizers at x1. X1 vector, yeah, right. And if that is not the case, we will see a subgradient in the second direction, which is a second basis vector. But irrespective of whichever of these two things happens, if you look at the span of both the initial point x0 is 0, g of x0 was just in the E1 direction, and this one could be either in E1 direction or E2 direction.
So this one, does it mean that it's like a lambda 1 E1 plus lambda 2 E2 this span?
Yeah, so this is just lambda 1 E1 plus lambda 2 E2. Yeah, maybe I should have described, yeah. Right. Yeah, so this is what the algorithm is. So the algorithm in this context is a map which takes at all the information and then figures out like which lambda 1, lambda 2 to use to query the gradient at. Yeah. So for example, here we saw that the initial gradient was gamma times E1, right? For gradient descent, it will do 0 minus gamma times E1. With some step size. So that's a gradient descent algorithm. So we are putting, say, step size times this gamma. So that will be lambda here. So that's a choice of the algorithm. But you can think of some other algorithm doing some other choice. And also gradient descent uses only the current points gradient, right? It does not reuse some past gradients. Here we are allowing the algorithm to reuse all the past gradients in whichever way it wants to use. So that's why we're talking about this span following. So these are more general class of algorithms, which includes gradient descent and pretty much like any of the first order methods that we can think of. Yeah. Okay. So the inductive argument is that at time step t, we will, like the span of all the things will include only E1, E2 all the way up to ET. Right? So span of
So does it mean that basically like when you are looking for the minimum of, finally you are looking for the minimum of that function,
yeah.
Right? So you're first looking at, you're basically instead of looking at this whole d-dimensional space, you are looking first along one component and then slowly you are increasing the dimension of the
That's
space
correct.
where you are looking at
Yeah, yeah.
And that dimension, finally you will not take it to D, it will be like the dimension where you are looking at the minimum, that's still less than the actual dimension of the X factor, right?
That's correct. It's as if like
So
you have a very high dimensional vector that you're maintaining, but you are searching in some subspaces for the minimum.
Some
Yeah.
direction you are basically ignoring.
Yeah, I'm ignoring because my oracle has not yet told me that that's an important direction. So the oracle, every time it gives me a vector, I know that this direction is an important direction. And I do need to pretty much cover all the different directions in order to know. So here, all the directions are important, right? Because we are taking a max over all the different dimensions. But the subgradient is only telling me that the first direction is important in the first iteration. Then once I do something in the first coordinate, it's telling me that the second direction is important. Then I go do something fixed in the second direction. Then it tells me that the third direction is important. So this iterative process basically means that until you do t+1 number of iterations, you'll not be able to find the minimum.
And you'll find the minimum in t+1 iteration.
In t+1?
Even if D is larger than t.
Yeah,
Right?
yeah. So here it only depends on t plus 1. Okay, that's correct.
But the second one depends on d, right? This x squared.
Yeah. So the optimum for this is given by something like the following. So it will be so the optimum in the ith coordinate is something like minus gamma over mu. So this is the optimum.
Because this other direction, since the 0 is the minimum.
0 is the minimum. So you just set them to 0.
Yeah.
But in the first t plus 1 directions, you have a linear component. So you want to set it to be negative. Okay. So this is the minimizer. And then we have a bound on what the function value is at this minimizer. But until you set all the coordinates in the first t plus 1 to be negative, the value will be at best 0. Because at least, so this is always positive, non-negative. And if you are not setting something to be negative in these coordinates, then it will be at least 0, right? So if you are only looking at subspaces, the minimum value is only 0 that you can attain. Whereas if you set all of them to be negative, then you get a reasonably negative value. So in the first t number of iterations, so there is a bound on how much optimality you will have. And that's basically the lower bound that we'll get from this.
Yeah.
Okay, so let me move on to smooth convex optimization. So any more questions I can answer?
And the convergence rate for this is going to be what?
This will be 1 over square root. So, so the upper bound that we had was so gradient descent is less than or equal to g times norm x0 minus x star divided by square root t, right? And the lower bound basically says for any algorithm, if you only have t iterations and d is larger and so on, then the lower bound is g So if you think of t being large enough, then this can be approximately looked at as square root t, right? So there is only a constant factor difference between both of them. So the upper bound is g times this divided by square root t, and the lower bound is g times this divided by 2 times square root t. Right? So basically we are saying, so this in particular says that you cannot get a g times this divided by t kind of convergence rate because that will contradict this one. Yeah. Okay, so let's come to smooth convex optimization. So in particular, like we make the following further assumption, which is smoothness. So a function f is said to be L smooth if so gradients are vectors. So this is just the L2 norm. Okay. So yesterday we only assumed that assume Lipschitzness, meaning that. So I think
I asked it yesterday, but let's to clarify.
Yeah.
So if I don't have the smoothness assumption, but we have a bound on the dimension, then
Yeah.
you can do better because this.
Yeah, so all of these are more dimension independent kind of
Right.
results.
Right.
Dimension dependent, there are more sophisticated methods like cutting plane methods,
Or
interior point methods. Yeah.
Yeah. Okay. Thank you.
Yeah, so Lipschitz in contrast is something like this. Or like we define. Right. So this is what we assumed yesterday in terms of Lipschitzness, but smoothness is a Lipschitzness assumption on the gradients themselves. Okay. So Lipschitzness was just directly assuming that the function value is Lipschitz, and smoothness is assuming that the gradients of the function are Lipschitz. Okay. Gradients are well defined and okay. So we have the following proposition. If f is L smooth, then f of y okay. So if f is L smooth, we have something like the Taylor second order Taylor approximation of the function, and we are saying that this kind of Taylor approximation actually upper bounds the function. Okay, and the proof is following.
So don't assume C2, right? Just C1. This means C1 plus gradient linkage. Automatically C1.
Yeah, I mean, for this to be well defined, gradients have to be well defined.
But not C2. You're not assuming.
No, the second derivatives need not exist.
Need not exist.
Yeah.
Thank
Yeah.
you.
So the idea is the following. So if you look at f of y, we can write it as f of x plus integral 0 to 1 grad f of x plus t times y minus x y minus x t. Right. This is just a fundamental theorem of calculus, and if you add and subtract grad f of x, so if you just look at this part, so using Cauchy-Schwarz, we can separate these. So this is Cauchy-Schwarz, and then we can use smoothness. So this is nothing but L times
You have a square root in the position.
Sorry?
Oh, no, that's a norm. Sorry.
Any questions? Okay, so now let's look at the performance of gradient descent. Gradient descent. So yesterday we saw like the convergence guarantee for gradient descent for Lipschitz convex functions. We did not use smoothness. So there we had a square root t here, g times norm of x0 minus x star divided by square root t. But for smooth functions, what we are able to get is that we are able to improve the convergence rate from 1 over square root t to 1 over t. Okay. The update is just this.
You mean in absolute value?
Which one?
In absolute value, or
so x star is the minimizer.
Oh, it's minimizer.
Yeah.
Yeah. Thank you.
Yeah. So this is the update for gradient descent. And we usually have a potential function or something to keep track of the progress that the algorithm is making. And here, for example, we can think of this as our potential function that we use to track the progress that we make. Okay, so xt. So if you look at the distance at tth iteration to x star, and then we see how much, like, does it reduce or increase or what happens with this. So we just expand the square here, and we see that this is nothing but xt minus x star square minus this is just expanding the square that we have here. And so if we recall from yesterday's proof, this is precisely the term that we use to get a bound on the function value, right? Because of convexity, we'll be able to bound this. The only additional term that we bounded by using the Lipschitz property was this term. And using smoothness, we'll actually be able to get a better bound on this term. And the reason is the following. So if you look at f of xt minus eta grad f of xt, by using this lemma, we can argue that this is less than or equal to f of xt plus grad f of xt inner product with minus eta grad f of xt plus L over 2 times minus eta grad f of xt square. and this is nothing but equal to f of xt minus okay. So in particular, this is a strictly descent method as long as eta is less than 1 over L.
So you're using this proposition, right?
Yeah, I'm using this proposition to like to get this bound. Okay. And so just rewriting these things. So we know that f of x star, because this is the minimizer, is less than or equal to f of xt minus eta grad f of xt, which is then less than or equal to f of xt minus eta times so in particular this implies that now let's plug this in xt plus 1 minus x star square. This is because of convexity. Plus so this is because of smoothness. Any questions on both of these terms? So the point is this one will bound using convexity and this term will bound using smoothness. Okay, so just recall that convexity tells us that f of x star is greater than or equal to f of xt grad f of xt. Okay. So this is the kind of term that appears there. So which is exactly what we are bounding using the f of xt minus f of x star. So that's this term. And then the second term was bounded using smoothness, and then this argument. Okay. So if we just combine both of these, because f of x t minus f of x star is common, so this is less than or equal to norm of x t minus x star square minus times 2 minus yeah. So if we choose eta equal to 1/3L, then this quantity will be 2 minus 1/1 minus 1/6. This is 2 minus 6. Right. So is less than or equal to 5/4 eta times
Sorry, why
Yeah.
choose such a specific value of eta?
I mean, we can choose anything. There is some trade-off that needs to be done. I want this to be positive and a constant. We can choose like this constant is not important.
Constant meaning constant in L.
No, L is like it has to be 1/L, but this 3 is not.
Yeah, the overall thing would be. Oh, I see. So we want eta L to be.
Eta L is actually the correct scale-free quantity, and there is a. So, for example, there is a eta in the denominator. So you want eta to be chosen as small as possible, so that this is not large. But if we choose eta to be very, very small, the bound will become very large. So you want eta to be large here. So we can choose an optimal thing, but it will change constants. But here I have chosen some, this is arbitrary.
It's just a bound, not necessarily the optimal. Right?
Yeah. So up to like constant and so on, like slightly different analysis can also give you slightly better constants. Yeah. Okay. So this, I mean, if we are convinced with this expression, then we just have to take a telescopic sum because these things cancel, right? And when we take an average here, we get like the desired bound. So taking average. And eta is chosen to be 1 over 3L. So it will be 15. Okay. And why is this average suboptimality useful? Actually, maybe this I also missed mentioning yesterday. Firstly, this means that there exists at least one point which achieves this, right? So in particular, and this is what we are getting upon. Right. So if we prove a bound on the average suboptimality, it means that there exists also at least one point within all the iterates that we have seen, which gets at least as good a suboptimality bound. So you can just pick the minimum among all the iterates, whichever iterate has the minimum function value. But in this context, because of this thing, we also see that gradient descent is actually monotonically decreasing the function value. So f of xt plus 1 is less than or equal to f of xt. So in this case in particular, we can even just take the last iterate. So this is actually equal to this is xt plus 1.
Why is it decreasing? Yeah. So this is xt plus 1, and that's negative. Okay. Because you're choosing that to be less than 1, etc.
That's correct. Yeah. So we are choosing eta to be say 1 over 3L or whatever. So this is a negative. Okay, so any questions at this point?
This L smooth is like when you're saying is that the Laplacian is bounded. Is it
The Hessian is bounded.
Hessian is
Second
bounded.
derivative is bounded.
Second derivative
Yeah.
bounded.
If it exists, it's bounded. That's
It's bounded,
basically.
and that's why this function is basically bounded from both upper, above, and below.
That's correct. That's
right.
Yeah.
And in this, in those kinds of function, basically this instead of 1 by square root of t, now you have 1 by t.
1 by t. That's correct. Yeah.
Okay. So if we keep on extending this argument to higher,
So there are results. So you can say that the second derivatives are bounded, meaning that if you put a Hessian here, and that thing here. Yeah. So if you have pth,
does that change that 1 by t to something?
Yeah. So again, there are two kinds of methods. One is the generalization of gradient descent. You can call it. I can maybe briefly mention the results, but I will not go into it. I'll just briefly mention the results.
So it's basically like if from the minimum this function increases slowly, then it's easier to find the minimum.
That's correct.
Right.
So I mean, what was happening in the earlier non-smooth thing was that gradient, your subgradient is telling you something, but even just you move a little bit, the subgradient completely changes. So you really have to get new information very often. And in these cases, we are seeing that the gradient does not change so quickly. So the gradient information at the given point is still meaningful in a reasonable ball around the current point, right? So you can use that to make a larger progress in every iteration as compared to the previous setting where we did not have that. Yeah.
The data is always positive, right? That's always nice. you're always moving towards one direction. Eta is always strictly positive.
Eta is always positive. That's why gradient descent. So
That's
you
why
move in the
this-
negative direction.
you're
Of,
only-
yeah. Yeah. Okay, so just going further in that direction. So gradient descent can be looked at in the following way. So xt plus 1 is argmin over x of xt So this is a quadratic problem, so we can write the solution of this explicitly in closed form. And it turns out that it's exactly the gradient descent. So this is a another way to. So this is equivalent to saying that, or this is exactly equal.
So you're continuing the same setup.
So maybe this is slightly an aside.
Okay.
So all I'm saying is gradient descent can also be seen in this other alternative form. Both of these are equivalent. Okay. Now, once we look at it in this form, then smoothness kind of seems to make a little more sense, particularly given this kind of expression. What we are saying is we have an upper bound on the function, right? So at the given point, we are taking an upper bound on the function. If we choose eta to be less than or equal to 1 over L, then this is indeed an upper bound on the function. And then the gradient descent is trying to minimize this upper bound. And you go to the next point, you make a new upper bound at xt plus 1, and then you again minimize that function. So gradient descent is trying to minimize these sequential upper bounds that you are getting at these new points and so on, right? Yeah. Yeah. So more roughly, so we have this, and then maybe you have this, and then you make a upper bound on the function, okay, with the gradient matching here. Something like this. Maybe I cannot draw proper pictures, but I hope the idea is clear that gradient descent is basically constructing new upper bounds of the function and then trying to minimize it. Now we can ask why are we using only first order Taylor approximation and then this kind of upper bound. We can go to say second order Taylor approximation and then use a different upper bound. So that would be so let's say second order descent. Would be the following. Okay. This is actually has a specific name. It's called Cubic-reg Newton's method. So here what we are doing is we are trying to construct even more accurate upper bound for the function. So we are looking at the Taylor expansion for until like the second order term. And then we are adding like a third order term to actually make it an upper bound because the action will change and so on, right? And this is called cubic-reg Newton's method. So for this, we assume that we only have smoothness of gradients, right? And there we got a 1 over T convergence rate. Here, if we, for this to actually make sense, even the Hessian has to be Lipschitz continuous. In that setting, we can actually get here 1 over t square convergence rate for this particular method. And in general, we can go to the pth order Taylor descent. Okay. Where we construct Taylor series expansion up to the pth derivatives, and then we regularize in the p plus 1th derivative to actually make it an upper bound. Okay. And this, and if the pth derivative is still Lipschitz continuous, under that assumption, we can again get a convergence rate which is 1 over p. Okay. So for p equal to 1, meaning that like the first derivatives are Lipschitz continuous, we got 1 over t. If second derivatives are continuous, then we again gradient descent itself may not give us like any improvement. But if we change the algorithm to also include like the second order derivative and so on, we get a 1 over t square convergence rate for this Cubic-reg Newton method. And for p to be larger, if the pth derivative is Lipschitz continuous, and then we take the generalization of this algorithm, that will get a convergence rate of 1 over t. Yeah.
Is it the case that one way of understanding these convergence rates is typically if you're just given a function to optimize, then the tunable parameter, if you're doing it numerically, is the learning rate?
Yeah.
So the better you can bound these derivatives, the more safely you can work with a higher learning rate without things blowing up. Is that? I mean,
here the algorithm itself is changing. Actually, it's not just learning rates that are changing.
No, I meant that if you, and like you said in that max example that you gave, even if you take a small step, the subgradients change very fast. So that means that we are not really free to choose a large learning rate because that will give us large steps.
Yeah.
But the better bounds we have on the derivatives, we can take we can quote unquote take larger steps.
Yeah. So for example, here, whatever your smoothness parameter L is, the step size we are taking depends only on L, right? It does not depend on the number of time steps. Whereas in the non-smooth case, it actually goes down as 1 over square root t, right? If you remember yesterday's calculation. Yeah, so smoothness enables us to take larger step sizes without the risk of overshooting in terms of function value.
Praneeth, I think this board is not visible beyond some point. So maybe just write a bit, start.
Like on top?
Yeah, I think that should be fine.
Okay.
And can you try using the white chalk maybe? Yeah.
Okay. So so we saw at least yesterday we saw that in the case of non-smooth convex optimization, 1 over square root t was what gradient descent got, and it turned out to be optimal. And today for smooth, we got 1 over t convergence rate for gradient descent, but it turns out that this is actually not the optimal rate. And there is a more sophisticated algorithm called Nesterov's accelerated gradient descent, which gets an optimal rate of 1 over t square. And again, like they also have extensions to these things. So for example, in the general case, this will become 1 over e to the 3p plus 1 over. Okay. So 3p plus 1 over 2 is always greater than or equal to p, because p is greater than or equal to 1, right? And yeah, so there is a general version like this, but in the remaining part, so let's try to get the 1 over t square convergence rate for Nesterov's accelerated.
Is that the lower bound or?
This is the upper bound.
No, the 1 by t square?
Yeah.
That's the lower bound, is it? Oh,
Is that the best you can do in that class?
Yeah, so there is both an upper bound and lower bound. I'll maybe do an upper bound.
Upper bound, okay. But the lower bound is also.
Lower bound is also there.
1 by t square, is it?
Yeah.
Okay.
Yeah. And actually, the construction for the non-smooth, the max over I, xi kind of thing, it can be smoothened in a way to again give the lower bound instance for 1 over t square for this setting also. But I'll maybe do only the upper bound.
Also, this one is 15 by 4 and that's 6 is just because of this eta, or I mean, this is of course true.
That's a crude bound. Yeah.
Okay.
Yeah.
Okay. So this is irrespective of what eta you choose, is it? Like it will be always less than 6. This is of course 15 by 4 is less than 6, but
yeah.
I'm saying that because that's for this particular eta, right?
So this theta also will have to choose. Yeah, 15 by 4 is less than or equal to.
Yeah. But I'm saying that.
Yeah, so maybe I should say there exists a choice of theta. So gradient descent also has a parameter.
Okay. So basically, gradient descent is just p equal to 1.
Yeah.
Because you don't have any smoothness assumption, that's the best you can do.
Yeah.
But convexity is crucial, right? So gradient descent to what?
Yeah, convexity is crucial for any of these.
Yeah, otherwise you will probably just stuck in one of the local methods, minimum, right?
Yeah.
It will fall in some trap or something.
Yeah.
Okay, so sorry.
So I have a question for mainly for you
Yeah.
guys. So there's something called saddle point approximation, right? So how is it related to this kind of thing? Sorry, can you repeat this?
No. If you do an integral, like exponential of some t times some function f of z, right? The t is very large, so depending on the sign, let's say minus t.
Okay.
So then it's dominated by just the minimum.
Oh,
So you're just finding the minimum, and the complex plane basically the minimum is there is not a global minimum, right? Because of this in the complex plane, right?
being
because
complex.
The second derivative is 0, right?
Right.
It's the minimum in one direction, the other direction is maximum.
Okay.
So if you go along the minimum, that path is also the steepest descent path.
Okay.
We are just doing the integral along that path.
Okay. Thank you. Minimum. Okay. No, that. Find the minimum. Okay. Thank you.
So the main idea behind Nesterov's accelerated gradient descent is the first observation that gradient descent is kind of a descent algorithm, meaning that it's always, so even when we look at this, it's always trying to construct an upper bound and then trying to minimize the upper bound. So it's always working with an upper bound for the function.
So this is UD Nesterov, the same Nesterov whose book you have referred to?
Yeah, that's correct. Yeah. So the first observation is that gradient descent always is looking at upper bounds to the function and trying to minimize upper bounds sequentially, right? The main idea behind Nesterov's accelerated gradient descent is that we can also consider lower bounds to the function, which are given by these things, right? So for any x, so if you any xt, right? If you look at f of xt plus grad f of xt times x minus xt, this is actually a lower bound on the function. Because like that, by definition of convexity, you take a gradient and then draw a hyperplane matching it at that point. It's actually a lower bound to the function. So the main idea behind Nesterov's accelerated gradient descent is to also use, in addition to the upper bounds, also to use the lower bounds. Okay. And how do we do the lower bounds? So initially we actually just start with point x0 and then a quadratic function like this. This is not exactly a lower bound, but we want to make this more and more like a lower bound by combining this with new lower bounds, meaning the following. So let's say we have phi k plus 1 of x to be defined as 1 minus alpha k times phi k of x plus alpha k times for some point yk So by convexity, this is a lower bound on the function, right? And we are taking a convex combination of the previous phi k and then the new lower bound. Initially, even though this may not be a lower bound, the hope is that this becomes more and more like a tighter lower bound because we are always keeping on combining it with lower bound functions. Okay. And to simplify notation, so let's define lambda 0 equal to 1 and lambda k plus 1 to be 1 minus alpha k times lambda. Okay. So now phi k plus 1 of x is so is less than or equal to lambda k plus 1 times phi 0 of x plus 1 minus lambda k plus 1 times f of x function. Okay. Because every time we are combining, yeah. So if we expand phi k of x in terms of all the things that have combined with it, and in terms of phi 0, the coefficient will be lambda k plus 1, and all the things that were combined otherwise are upper bounded by f of x. Okay. Okay, so let us say we denote phi k of x. So phi 0 of x is a quadratic and we are always combining it with linear functions, right? So phi k of x is always a quadratic function, and any quadratic function can be written as the following.
This alpha k's are just some.
Yeah, alpha k I have not defined. So let me instantiate all of these towards the end. But all I'm saying is these are some parameters within the algorithm. And the main intuition is that we want to keep combining it with lower bounds. And then alpha k are the parameters that we'll choose later to see how well the algorithm can do.
And
And
basically tune all the alpha k's.
Yeah. Okay. So inductively, we can easily show that phi k of x has this particular form. Okay. Because firstly, as we mentioned, phi k is always a quadratic function. Because phi 0 was quadratic, we're only combining it with linear functions. So the resulting function is always a quadratic. And the quotient in front of the quadratic.
What is
Sorry?
phi k star?
I'm saying we are defining phi k. I'm saying phi k of x will have this form.
Okay.
Where phi k star is the minimizer of phi k of x, and phi k star is the minimum value, and vk is the minimizer of phi k of x.
Okay.
So the reason why we are doing all of this and thinking about in this form is the following. If there exists xk such that f of xk is less than or equal to phi k star, then f of xk minus f of x star is less than or equal to lambda k times phi 0 of x star minus f of x star. Yeah.
Will you choose alpha k so that this is ensured or something like that? So how do you know that this will always?
No. So there is a condition here. So this itself, as we'll see, is not very difficult to show.
Oh.
But the challenge is to
how will you ensure the condition?
Find, yeah. So that's the main challenge. So that will come to next.
Okay.
So right now, this claim is only trying to motivate why we are even thinking about this thing.
Okay.
The thing is, if we why are we constructing this phi k and why are we doing all of this? Because if we can simultaneously update this phi k of x as well as find this xk which satisfies this property, then it's telling that as that can have a suboptimality bound. Yeah. So f of xk minus f of x star. So this is less than or equal to phi k star minus f of x star, and phi k star is the minimum. So we can say this is less than or equal to phi k of x star minus f of x star, and phi k we have this bound. So this is less than or equal to lambda k phi 0 of x star plus 1 minus lambda k f of x star minus f of x star. Okay.
So the definition of phi kx.
Sorry?
In the definition of phi kx, phi k star is basically phi k evaluated at vk. Is that
Phi k evaluated at
vk in the definition of phi kx?
Okay, so I'm saying that it has this following form for appropriate phi k star and vk.
Which are not determined.
Which can be determined explicitly using this update and so on. I'm just using them as notation here. Yeah.
So how do you get that phi k star is less than or equal to phi k of x star?
Because phi k star is the minimizer, right? So we set anything here.
Oh, that's not changing. Okay. That's good to get. Okay.
Yeah. Okay, so if we just look at this lemma, we see that there are two things that are required for us to get a good algorithm. The first one is that lambda k should decrease very, very rapidly, right? The faster it decreases, the better for us. At the same time, every iteration, we should be able to find an xk such that f of xk is less than or equal to phi k star, right? So these are the two requirements. So how do we go about it? So in order to understand this, so let's look at what pk star and vk actually look like, okay, just from this update equation. And this is basically some computation. So yeah. Okay, so the expressions are a bit complicated, but they're actually not difficult to obtain. So I'll just do that here. So phi k plus 1 of x is 1 minus alpha k times phi k, and we're saying it has the following form. Okay, so if you take the terms involved, okay, so this we are saying is,
Sorry, Praneeth, what was yk?
so yk is the point that we are querying the gradient at. So the algorithm has not yet been fully instantiated. So the idea would be that we'll query the gradient at yk, right? And then we will have f of yk and then grad f of yk. We can maintain this estimate phi k plus 1 of x.
So yk is the iterate of the x naught.
There are actually maybe 2 iterates that we'll be maintaining, but yk is the point at which we'll query the gradient.
Okay, so what is, like, if when I start, I mean, this process, so let's say I start with x naught and I build phi naught. Now,
Yeah.
if I want phi 1, what do I put for
So,
y?
so if you want the algorithm, so let me describe the algorithm.
Case will have to be chosen, etc. So that will come through the proof, perhaps.
And the yk also will come from the proof, is it?
Yeah. So like the algorithm itself might look very like out of thin air or something. So the proof will clarify why we are doing something like this, but the algorithm will roughly look like this. So we'll have two iterates x0 and v0. So initially we start with x0 equal to v0, and yeah, so we have started with this. So actually the alphas here and there might be different. So let me just write it. So the algorithm is of this form. Okay. So we start with x0 equal to v0. We pick a yk which is in the linear combination of xk and vk. Okay. And then the new xk plus 1 will be gotten by doing gradient descent on yk. And the new vk plus 1 will be gotten by using the gradient at yk, but taking a descent step from vk. And then like this is also different from this. This is also important. Okay, but like why this precise form and so on, that's what hopefully will be clear with this argument.
Basically, you are making better and better lower bounds.
That's correct, yeah. In some sense, xk is something like an upper bound.
Right.
You always trying to decrease, and vk is like the lower bound. Yeah, this vk basically it's minimized at vk. So the quadratic centered at vk with this particular curvature, so that's the lower bound that you have. So you're simultaneously trying to improve both the upper and lower bounds. Yeah. So yeah, so basically vk plus 1 has is defined to be this, right? And we are saying because this is a quadratic, it'll have quadratic with like identity Hessian here, right? So it'll be of this particular form. The only thing is like what are the quantities vk plus 1 star and vk plus 1, and how can we compute them from this? So if we expand only the terms with respect like that have an x here, so the x square term will exactly match this one. Okay, and there'll be something times x. The term here will be okay. So if we try to, is this clear? So we expand this, there will be terms which will have a norm of x square. and there will be terms which will have inner product of x with a vector, and then there will be constant terms, right? So the term which has norm of x square, the coefficient will be 1 minus alpha k lambda k L over 2. Okay, 1 minus alpha k lambda k L over 2, that will give us norm x square. This does not have a norm x square. And then we look at terms which have an inner product with x. So there will be minus 2vk inner product with x times lambda k L over 2 times 1 minus alpha k. So that's this term. This will have one term which has inner product with x, that will be alpha k times grad f of yk. That's this term. I think there has to be minus. Okay. So basically, if we complete the square here, meaning that, so we'll take this quantity out. So we have a norm x square plus this term. This is nothing but equal to norm of x minus this quantity square minus we just put in the missing square term, right? So this part, if we look at carefully here, that's exactly the vk plus 1 that we wrote there, right? So this, and then we need to just collect the constants now. So we have taken the norm x square term, we have taken the term which involves like inner product with x, right? The only terms that are left here are the constant terms, and then this is another constant term that will be added to it. And all of them, if we put together, that's what will give us this vk plus 1 star.
So what's your assumption here on the function f?
Yeah, so I have not come to it yet. So the assumption here will be precisely that the function is L smooth, because that was the setting that we were looking. L smooth. Yeah.
Just L smooth.
Yeah. Okay. So given that we have this phi k plus 1 star, yeah. So I have not computed phi k plus 1 star explicitly, but like if we just collect the constant terms from here, and then this is the extra constant term, you can trust me. I also verify that phi k plus 1 star will exactly be the quantity that's written over there. So the point is next to find an xk plus 1 such that f of xk plus 1 is less than or equal to pk plus 1 star, right? And for this, it turns out, because yeah, this is where we use the assumption that the function is L smooth, and we saw earlier that gradient descent is actually a decreasing operation. So it's a descent algorithm. So every time it decreases a function value. So we'll choose xk plus 1 to be yk minus eta grad f of yk.
So that was true under L smoothness, right? That is
Yeah.
why you need L smoothness.
That's where we'll use L smoothness, and eta is less than or equal to 1 over L. Okay. So in this case, we'll get that f of xk plus 1 is less than or equal to f of yk minus eta over 2 norm grad f of yk square. Okay, so this is just using L smoothness of the function and then using like the gradient descent property, right? Now the claim that we want to see is that this is actually gives us something like this. So if you look at f of xk plus 1 minus phi k plus 1 star. So this is less than or equal to f of yk minus eta over 2 norm grad f of yk square minus, so phi k plus 1 star we have written there, so we can write the exact thing. Okay, so I have just put in the value of phi k plus 1 star that we computed there, and we have a phi k star in that expression, and
So
phi k star I have replaced with f of xk because we know that f of xk is less than or equal to phi k star by the inductive assumption.
You're doing inductively. Okay.
Yeah. Okay. Right. So we can just rearrange terms. Okay, so I have just collected three different terms. So one is f of k minus f of xk. The other one is includes norm of gradient square, like these are the two terms. And then finally one thing which has inner product with grad f of yk, right? So if we use convexity here, we know that this is less than or equal to 1 minus alpha k grad f of yk times yk minus xk, and then this has a very similar term. So here, if we choose yk to be equal to 1 minus alpha k xk plus alpha k vk, then this term goes away because this is equal to grad f of yk times yk minus 1 minus alpha k xk minus alpha k vk. Okay, so if you choose yk to be exactly as this linear combination, this term just disappears and we'll only have this term. And if we choose alpha k square divided by lambda k 1 minus alpha k times L to be less than or equal to eta, then this is a negative term. Okay, and the previous condition that we used here was that eta is less than or equal to 1 over L. Okay. Okay. So this was a bound on f of xk plus 1 minus pk plus 1 star. So the point is, if this thing can be shown to be negative, we will be able to find an xk plus 1 which satisfies this condition, and then we can use this within this claim. So at every time step we have an xk which satisfies this property, and then finally that point will also satisfy this kind of suboptimality guarantee, right? So the question is, how do we choose these alpha k's and lambdas and so on so that this is satisfied? So because we want alpha k's to be as large as possible, which will then decrease lambda k, we will choose alpha k to be the largest root of this equation. Okay. So if we do this, then if we denote ak to be 1 over square root of lambda k, then ak plus 1 minus ak so this is lambda k minus lambda k plus 1 so this is equal to alpha k
So you want the lambda case to be small so that you can get a good rate there, right? Because these inequalities. The first, in the proof of claim, you have these inequalities.
Yeah.
You want
This claim. Yeah. So yeah, so we want lambda to be as small as possible so that we'll get a very good rate. And lambda k is given by 1 minus alpha k minus 1 times alpha k minus 1 to be as big as possible, smaller than 1. So we are choosing alpha k to be the largest thing that can satisfy this condition. Okay, and then we will get this condition, and yeah, so this is precisely this condition. So this thing is nothing but lambda k plus 1. Okay, so the square root of this thing is equal to 1. So this is equal to, right? So what we are seeing here is that so ak plus 1 minus ak is greater than or equal to half, implies ak plus 1 is greater than or equal to k plus 1 over 2. Right? Ak plus 1 was 1 over square root lambda. So this implies that lambda k plus 1 is less than or equal to 4 over k plus 1 whole square. Right? And now if you put that here, we are getting something about the initial suboptimality divided by k square.
So get 1 over k. Then.
1 over, yeah. 1 over k square is the rate.
But when you sum, then you'll have to have.
We don't have to do the sum. So this is directly the suboptimality of the kth iteration.
Right. Okay. Right.
Yeah.
Not the difference.
Yeah. So this is all like this is all in static terms. There is no iterates involved.
Wow.
Yeah, and it turns out that at least in this setting, this 1 over k square is indeed optimal.
And just L smoothness is good enough.
No, under the L smoothness assumption,
Yeah.
1 over k square is basically the best you can get.
The rate,
Yeah.
And
Yeah.
this algorithm.
And this algorithm achieves that rate. So now hopefully like the algorithm also makes sense. So we chose yk to be precisely this 1 minus alpha xk plus alpha k vk. And then vk plus 1, so xk plus 1 was gradient descent at yk. And then vk plus 1 is vk minus some other step size times grad f of yk.
I mean, just gradient descent you have achieved only under the second Taylor descent.
That's correct. And also the algorithm will need to look at the Hessian.
Exactly.
Yeah.
So it is less assumption, but the algorithm is.
Yeah.
taken care of.
Yeah.
So this in the algorithm, how is alpha case? How do they?
Yeah. So there are also closed form solutions. So you can. So here we are choosing it in this form.
Okay.
So lambda 0 is equal to 1. So then you have alpha 0 square times 1 minus alpha 0 is equal to 1. So we can see that when alpha 0 is equal to 0, this is actually 0, right? And when alpha 0 is equal to 1 or close to 1, this actually goes to infinity. So it has to cross 1 at some point. So we'll pick the point where it's actually equal to 1. Yeah, maybe I'll stop here.
So if you look at his book, the algorithm is also stated.
Yeah, it's stated in precisely this way. Yeah.
Thank you.
There are many different modifications depending on, like you have two iterated xk, y, vk, and so on, right? So you can write it also in different ways. All of them are equivalent, and there are also slightly different proofs, but still, to a large extent, people think of this mostly in this algebraic way, except for the high-level intuition of looking at upper bounds, lower bounds, and trying to minimize both. Most of the treatments still are more algebraic, and you have to work through these expressions and so on.
Solve the
Yeah.
equations, etc.
Yeah.
Very nice.
Sounds. Yeah.
So tomorrow you'll do stochastic gradient descent.
Yeah. Tomorrow I'll talk about stochastic.
Thank you.
So let's break for lunch. We'll meet again at 2.